Thank you very much. So I will speak about joint work with Toby Gee and David Savitt. So a little bit of notation. So P will denote a prime number. And I want to fix embeddings of Q bar into C and into QP bar. And I'll use gamma sub a field to denote the absolute Galois group of that field. So especially gamma of, in particular, gamma of Q is the Galois group of Q. And the embedding gives a decomposition group at our prime P. And then inside that, there's the inertia subgroup I of P. OK, so I'll start by recalling the rough statement of Serre's conjecture. So given a mod P Galois representation of dimension 2 of the absolute Galois group of Q, that is odd and irreducible, there exists an eigenform F of a certain weight k question mark of rho bar, an integer which is an integer greater or equal to 2, and level gamma 1 of n question mark of rho, where n question of rho bar, where n question mark of rho bar is an prime to p integer, positive integer, such that rho bar is isomorphic to the Galois representation, to the mod P Galois representation of that eigenform. So, in other words, it's on the one hand saying that just some simple condition, namely irreducible and odd, which means that the eigenvalues of complex conjugation in the Galois group are 1 and -1. That odd and irreducible imply that rho bar is modular, arises from a modular eigenform. But it's even more specific than that. It also says that it arises from an eigenform in a particular weight, which I'm not going to define explicitly, and a particular level. And I will not focus on the level at all in what follows, when I'll also talk about generalizations of this conjecture, but rather on the weight. In fact, on the weights of a given modular modular Galois representation. So one remark I want to make is that, so even though I don't give the definition, which Serre gave as a combinatorial recipe in terms of, well, not in terms of the whole Galois representation, but only in terms of the restriction of rho bar on inertia at P. Okay, and this conjecture has recently been proved by the work of Serre, Berger, and Kissin. Okay, so next I want to talk about a reformulation of this conjecture, which can be found, for example, in a paper of Ash and Stevens. So for that, fix an irreducible mod P Galois representation and some level that's prime to P, some positive integer that's prime to P. Then rho bar is modular of weight k and level n, if and only if rho bar occurs in the following cohomology group. I'll take group cohomology of gamma 1 of n, and let gamma 1 of n, which is a subgroup of SL2Z, act via its reduction to SL2FP, or to GL2FP, on sim k minus 2 of FP bar squared. And what I mean by occurs is the exact analog of rho bar isomorphic to rho bar f, namely the characteristic polynomials of Frobenius elements of the Galois representation outside P and N match the polynomials you get in terms of the Hecke eigenvalues of a Hecke eigenvector in this cohomology group. So one has the same Hecke algebra that acts on a space of mod P modular forms, also acts on this group cohomology group. Still double coset operators act on this cohomology group in the usual way. So occurs just means the Hecke eigenvalues are determined in terms of the Frobenius characteristic polynomials and vice versa. And now, once one knows that, which is something one gets from the Eichler-Shimura isomorphism, when k is large, this representation of GL2FP, sim k minus 2, is not irreducible, but it breaks up into many pieces in general. So this is in fact equivalent to rho bar occurring in H1 with coefficients 1 of the irreducible constituents. So for some f a Jordan-Hölder constituent of sim k minus 2 of FP bar squared as GL2 FP representation. So the important thing is not that I'm using group cohomology, it's just a convenient way to express things, but that instead of thinking about weight k as in Serre's original statement, one can rather think in terms of these weights f. So the definition is, I mean, not just that one can think in terms of those, but that it's more natural to think in terms of the f's. So a Serre weight is an irreducible representation of GL2FP over FP bar. So that's a finite group. It has finitely many irreducible representations, and explicitly one can all write them down in the following way. I let f a comma b be the symmetric eighth power of the standard representation. Sorry, the a minus bth power of the standard representation twisted by the bth power of the determinant, where a and b are integers that whose difference is between 0 and p minus 1. And for b it doesn't matter, but one could take b between 0 and strictly less than p minus 1. In that way, one lists every such representation exactly once. So these are the Serre weights explicitly. And then, rather than asking about the integer k, one can take here, I mean, Serre really described the smallest possible integer k one could take here. Instead of that, one can now let weight of rho bar be the set of all f's that can be taken here in the last line. So weight rho bar is the set of all Serre weights f such that rho bar occurs in H1 gamma 1n comma f for some n. I will not worry about the levels. For some n that's prime to p. Okay, let me even write this down. I should have written this over there. Yeah, in fact, is it? Or here, I guess. So we see the following from these equivalent statements up there, that for 2 less than or equal to k less than or equal to p plus 1, sim k minus 2 is actually irreducible. It's actually a Serre weight. It's actually irreducible as GL2FP representation. So one gets that sim k minus 2 is a weight of rho, implies that rho bar is modular of weight k and level prime to p plus some level prime to p. And then this implies that rho bar restricted to the decomposition group at p has a crystalline lift to a p-adic Galois representation. So if that's dp is the p-adic Galois group, has a crystalline lift of Hodge-Tate weights k minus 1, 0. The reason is that rho bar is modular of weight k means we have an eigenform of weight k and level prime to p. We can look at the corresponding p-adic Galois representation. That's going to be crystalline since the level is prime to p. And it has Hodge-Tate weights k minus 1 and 0 because the modular form has weight k by Dulin-Entfaltungs. Okay, but in fact one can now get a statement for all Serre weights of this form by twisting by powers of determinant on the representation theory side and by powers of cyclotomic character on the Galois side, and one gets that. So after twisting, the upshot is that f a comma b is a Serre weight of rho bar, implies that rho bar restricted to decomposition at p has a crystalline lift of Hodge-Tate weights a minus 1 comma b. So there's just a shift by 1 going on. And the remark is that this implication is in fact an equivalence. In fact, this is if and only if. So the philosophy is that if you have a local crystalline lift of a given Hodge-Tate weight, in fact, it should be explained by the existence of a global lift of that Hodge-Tate weight, which is crystalline and ramified almost everywhere. And then by Fontaine-Mazer-Langlands, this gives rise to a classical modular form of that weight and level prime to p, and one gets that. Thank you. Yes, that I just copied from up there. That was a mistake. Well, in fact, now that Serre's conjecture is a theorem, one can also verify that this is an equivalence because enough p-adic Hodge theory is known that one can explicitly determine the mod p Galois representations one gets as reductions of crystalline representations of these Hodge-Tate weights. And now to make this more concrete in this GL2 case, if rho bar restricted to decomposition at p is semi-simple, that then one can actually describe some crystalline lifts explicitly, and they sort of explain some Serre weights. So there are two cases. Rho bar could be a sum of two characters, or it could be irreducible. And if it's a sum of two characters, first of all, so, okay, I'll use the following notation. So I'll write it first. lambda epsilon bar to the A and mu epsilon bar to the B, where epsilon is the cyclotomic character, and lambda and mu are ramified characters, so they don't change the Hodge-Tate weights. They don't change the fact that the representation is. I didn't say that. So epsilon is cyclotomic, and these are unramified mod P characters. And I want to assume that A minus B is strictly between 1 and P minus 2. This covers almost all cases. I guess A minus B could be as low as 0 and as big as P minus 2. But in this case, we have the following crystalline lifts. First of all, we have, well, sort of the most obvious one you could take is just take a Teich-Müller lift of the unramified character and epsilon to the A. That's a crystalline character of Hodge-Tate weight A. So the Hodge-Tate weight is A. And then the second one I can lift as mu tilde. That's an unramified character. It has Hodge-Tate weight 0 times epsilon to the B. That has Hodge-Tate weight B. So this is one crystalline lift. And it corresponds to the fact that f A minus 1 comma B is a Serre weight of rho bar. And then one can do something else. One can lift the first character as before, but the second character we can lift to epsilon to the B plus P minus 1, because epsilon bar has order P minus 1. And this has Hodge-Tate weight, Hodge-Tate weights A and B plus P minus 1. So the corresponding Serre weight is, if you order them, the Hodge-Tate weights correctly, it's B plus P minus 2, comma A. And now the fact that now the assumption that A minus B is in that range guarantees that these are in fact the only two Serre weights of that Galois representation. Otherwise, in the boundary cases, one gets slightly more. One gets one more, maybe. And I don't think I have the time to give the case when rho bar is locally irreducible in all details, but let me just indicate that if rho bar restricted to decomposition at P is irreducible, then we can, then in fact it's isomorphic. I mean, it's still very simple. It's just an induction of a character. So it's an induction of a character from QP squared to a character of the Galois group of QP. Well, it's one of Serre's tame fundamental characters to some integer power. And then maybe one has to twist by some unramified character. And the way one can lift this is one just lifts. One can now lift this inducing character to crystalline characters. And again, in this way, one will be able to describe two, essentially, two crystalline lifts that give rise to, or that correspond to two different weights of rho bar, and these are the two the two Serre weights of rho bar. There are two always in this case. Okay. So this is what I wanted to say about GL2. Any questions before I move on? Okay, so I'll start with the general setup.
So what happens if it's in the singular range?
You mean here?
Yeah. Can you still find explicit lift?
Yes. For example, if it's 1, then you get Hodge-Tate weights. Let's say it's A is 1 and B is 0. Then you get Hodge-Tate weights 1 and 0 in this way. But instead of 1 and 0, you could take P and 0, which gives rise to Fp minus 1, 0. Yes, you can still all describe them that way. Yes, and another thing maybe I could remark is that, of course, one could add P minus 1 to both A and B, but that would not change anything in the Serre weight, because in the Serre weight we don't literally use A, we just use A minus B. All right, so now for the general setup. So there will be some notation I have to introduce. First of all, okay, so I'll start with what Serre weights are and some related definitions. So for this, I will just, this is purely local. I take a connected reductive group, split connected reductive group over ZP. If you want, you could take GLN. And then inside G, I fix a split maximal torus T, and in between a Borel subgroup. And now I'll define, well, two kind of representations. So if lambda is a dominant weight, so a dominant character of the maximal torus, then let W of lambda, I maybe need some space. So let W lambda be the irreducible representation of the group considered over QP bar, so the generic fiber, of highest weight lambda. And let F of, yeah, okay, I'll write this right here. But I don't want to consider it as representation of the algebraic group. What I want in the end is I want to consider it, well, I can think of it as a finite dimensional QP bar vector space with an action of the QP bar points of that group. But I want to restrict it to the ZP points of that group. So considered as G of ZP representation. Okay, so that gives one representation, and then I want to do the same thing, but now in characteristic P. I want to take the irreducible representation of the special fiber of the group G over FP bar of highest weight lambda. So in characteristic P, the representations of a reductive algebraic group are still parameterized by highest weights, but in general they would be smaller than what you see in characteristic 0. But again, I want to consider it as G of ZP representation, just via the map as before from the ZP points to the FP points. I map to G of FP, and that acts on this FP bar vector space. And now there's one more definition before I describe Serre weights. So x1 of t is the subset of the dominant weights. Well, they will not automatically be dominant, such that when we pair this character against any simple co-root, we get an integer between 0 and p minus 1. So this is just the analog of what I had for these pairs a comma b, that their difference is between 0 and p minus 1. So for GLN, it would just literally mean consecutive differences of an n-tuple of integers being between 0 and p minus 1. And then the fact is that these highest weights give us the Serre weights. So the fact due to Steinberg is that at least supposing that the derived subgroup of G is simply connected, which is the case for GLN, for example, because SLN is simply connected, then the irreducible representations of G of Fp over Fp bar. So this is what I mean by Serre weights. It's completely the analog of what I had for GL2 before. Is equal to the representations f of lambda, where lambda is in x1 of t. Yes, I mean, I could consider, remember that f of lambda, I considered it as G of ZP representation, but via its map to GFP bar, GFP, I could equally well consider it as GFP representations. And one remark is that the right-hand side might be infinite if the group is not semi-simple, but it's also easy to describe when two such representations become isomorphic as G of Fp representations. It's like the determinant twist for GL2. That was ambiguous. And one example. So for GL2, W of A comma B is just the symmetric A minus B bth power of the standard representation twisted by determinant to the B. That's what the irreducible representations of the algebraic group are in characteristic 0. In characteristic P, they are more complicated, but at least so this is for all A greater or equal to B, but if AB is in x1 of t, then if we reduce a lattice in WAB, we get FAB, sim A minus B FP bar squared tensor determinant to the B. And explicitly, this is just a condition of before, that A minus B is between 0 and P minus 1. Okay. And now the one other ingredient I'm going to need, some more notation. Is about Hodge-Tate weights in the setting when, because we will have Galois representations into L groups or into dual groups, so I need to make sense of Hodge-Tate weights in this setting. So in fact, what one gets are Hodge-Tate co-characters as follows. So let G hat be the dual group of G. So it's still GLN if G was GLN, for example. And T hat a maximal torus, or maybe the maximal torus one used to define it. Now suppose we're given a p-adic Galois representation into the dual group. First of all, we'll say it's crystalline if, well, we know what this means when or it's known what this means when the dual group is GLN, but we'll say it's crystalline if when we compose, so if R composed with rho is crystalline for all algebraic representations R from G hat to GLN. So then you get the representation into GLN Q bar, and then it's the old notion of crystalline. And in fact, it's enough to take one if it's faithful. Any question? And now in that case, so if, okay, one doesn't quite need crystalline, but in particular in this crystalline case, one has Hodge-Tate weights, a Hodge-Tate co-character as follows, or rather a conjugacy class of Hodge-Tate co-characters. There exists a unique Hodge-Tate co-character conjugacy class of rho. I'll write HD underlined. So it's a homomorphism of Gm into G hat. So this is over QP bar up to G hat conjugacy. And if we have such a map of this rank 1 torus into G hat, we can always conjugate it into our given maximal torus. So then it's just a co-character of the torus up to the Weil group of the dual group. So in particular for GLN, co-characters into the dual torus are just n tuples of integers, and the Weil group is Sn. So it's just a multiset of n integers, as before. And then the property that characterizes these Hodge-Tate co-characters is that whenever we compose with an algebraic representation R, so R composed with, I just composed the character from Gm further into GLN, then this as multiset of integers is just the usual Hodge-Tate weights of R composed with rho. So for all R. And I think this goes back to old work of Serre, in fact. Although maybe in full generality, this is in the paper of Buzzard and Gee. Now, yes?
Crystalline property on adjoint representation, for example?
On one, you mean?
True that
Or
rho is crystalline in this sense if and only if the adjoint representation.
you just need one faithful one.
You need one faithful G. So
If
if G is faithful,
well, then it's faithful, and then. Okay, yes. If it's adjoint, yes. Okay, if it.
So is it true or
No, it's false in general.
if you twist by like a ramified quadratic character, you twist by ramified quadratic character, that's killed in taking the
for
adjoint.
semi-simple.
Semi-simple adjoint. Or
You have to have that Hodge-Tate parameters are compatible with your situation. Yeah. Oh, it's not true.
I think it's enough to check for one faithful one. But
Yeah,
Yeah.
the adjoint is not.
The adjoint is not faithful.
it's not faithful in general, yes. But if it's semi-simple and adjoint, then it is. So. Okay, so now I want to go to the global context and consider a reductive group over Q. So I'm just taking Q for simplicity of notations. One could take a number field, an arbitrary number field. So connected reductive group such that, well, I want to demand the following conditions. First of all, as before, that the derived subgroup is simply connected. I want to demand that at least over QP, the group is split. So then we are back locally at P, we are back in the setting I had before. And it will also be convenient to demand that G of I is compact. It's not necessary for making conjectures about weights of Galois representations, but one can say more in this compact case. It's easier to lift to characteristic 0, etc. Or it's possible to lift to characteristic 0, etc. And then the final assumption is that there exists a twisting element eta in which is a character of the torus that is Galois invariant, where k is q, such that, I mean, it's an analog of rho, the half sum of positive roots. So it's a character that pairs with all simple co-roots to 1. Okay. I guess I fix one. I think I need to fix that even to define the dual group. I need to fix a pinning of the group.
But is this action of gamma corresponding to something by automorphism?
Or in fact, I think what one can do in order to avoid the choice is one can take a limit over all choices.
Yes,
This is
but then it's only to order automorphism. But you will not have to do parallel over Q if you want compact. But indeed you can speak of C maximal torus with
yes.
isomorphic T of an algebraic clover. What do you
Yes, I mean, I always want to. Yes, I'm not sure I can say anything sensible now, but.
But it will be correspond to something for the dual group, for instance.
Right, we will use it for the dual group. Yes. That's where it will come in a moment. And this condition is satisfied, at least, for example, when G is a compact form of UN and N is odd. Otherwise, one doesn't have the twisting element. And now I want to consider the analog of a space of modular forms. And this is where compactness makes things easier, because one can consider algebraic automorphic forms. And I won't write down the definition, but it's essentially functions on a adelic quotient of G, on a suitable adelic quotient of G, where the coefficients, the values of these functions, land in some G of ZP module. And U will be a level that's prime to P. Yes, I mean, secretly, okay, if I'm maybe not being completely precise here, one should fix a model over the integers of the group, and then one gets G of ZP, and one can make sense of U being a product of G of ZP at P and an open compact subgroup away from P. And I want to take the level also sufficiently small. And now what coefficients do I take for M? So for M, there are two coefficients that I want to consider, namely either I want to take W of lambda, which is a G of ZP module, if you remember, where lambda is any dominant character of the torus. So this is the analog of a, in this case one gets the analog of a space of classical modular forms. So classical weight, or I'll take f of lambda as Serre weight, where lambda is an x1 of T. So this is Serre weight. And now there's a conjecture due to Buzzard and G that conjecturally, if one has a Hecke eigenvector in this space of algebraic automorphic forms, then there is an associated Galois representation as follows. So a Hecke eigenvector in SU, well, in the p-adic space SUW lambda has an associated Galois representation rho from the Galois group of Q to the L group G hat QP bar semi-direct the Galois group of Q such that, well, that is crystalline since the level is assumed to be prime to P and the Hodge-Tate co-characters are given by the conjugacy class of lambda plus eta. So this is the twisting element eta. And the remark is that lambda plus eta is a priori a co-character of T, but we can think of it as a character of T, we can think of it as co-character of T hat. So this is a recent conjecture of David Savitt. And I also want to make the remark that when G is equal to UN with n odd, then one knows now that such a Galois representation exists due to the work of Shin, Cluzel, Harris, Labesse, and others. So now for the purpose of making a generalization of Serre's conjecture, suppose we give him a mod P Galois representation into the L group over Fp bar. That is irreducible and assumed to be modular. That means it should arise from one of those spaces where, for example, M is one of those F lambdas, or there are other ways of saying that too. In that case, we can let the weight set of rho bar be all the Serre weights F of lambda, such that rho bar occurs in SU F lambda for some U that is, as before, of level prime to P. And then the first conjecture is that the analog of the statement I had on the board before for GL2, namely that whether F lambda is a weight or not is determined by whether there is a local crystalline lift of corresponding Hodge-Tate weights. Yes.
It's to simplify matters, or
it's to have a Galois representation.
Yeah. So if there is no
Conjectural Galois representation, at least. You see, the problem is that this is what David Gee clarified: is that there are two notions of algebraic automorphic representations, and sort of the one that behaves well in functorialities and should have Galois representations is different from the one you see in the cohomology. You could go to a, you can pass to a covering group where the problem goes away, but on the group itself, you might not be able to have the Galois representation into the L group of your group.
But there is a more general statement when you don't have any twisting element, when you replace G hat by something, right?
Well, then, I mean, in general, you will have to make some choice to pass to a covering group. I don't know whether you could get such a nice statement, such a clean statement.
So you look for a covering of index 2, right?
No, what do you mean by index 2?
Twisting element,
It's something like a GM, but maybe one has to do a little more. I think, if I remember correctly, one might have to I thought there were 2 steps one might have to make. In one step it was canonical, I think, but I don't remember exactly now. But for example, in the case of Harris-Taylor, you do have an extra GM, which is there somehow because you don't have the twisting element in general.
What does robot occur?
Sorry?
What does this mean, robot occurs in SU?
Well, it means that, it's a matching of Satake parameters away from, at good places.
What does irreducible?
Well, irreducible means that it's not contained in, okay, let's say, yes, I think, what we mean is that it's not in any parabolic that is preserved by the Galois action. Up to conjugacy. Now fix, for the first conjecture, fix a weight lambda in x1 of t. Then f of lambda is a weight of rho bar if and only if rho bar restricted to decomposition at p has a crystalline lift of Hodge-Tate weights, the conjugacy class of lambda plus eta. Maybe I should say, okay, I think that's okay. And so one direction is implied by the conjecture of Bassett and Gee. If f of lambda is a weight, one can lift to characteristic 0 due to the assumption that G is compact at infinity, and then one has a p-adic Galois representation of, global Galois representation of this Hodge-Tate weight. And I should also say that a conjecture like this was first made for GLN by Toby Gee. But the other direction is maybe not so clear, and in fact, the statement of this conjecture implies a further conjecture, namely, so in general, due to the fact that the reduction of W lambda is bigger than f of lambda, the conjecture of Bassett and Gee plus conjecture A imply the following conjecture B, that if lambda and mu are 2 weights in x1 of t such that f of lambda is a Jordan-Hölder constituent of the reduction of W mu, then f lambda is a weight of rho bar, implies f of mu is a weight of rho bar. So this is something one doesn't see for GL2, because for GL2, if f lambda is a constituent of the reduction of W mu, then lambda is equal to mu. Okay, and finally I want to say something about an explicit version of this conjecture, provided, as in the example I gave before for GL2, provided that rho bar restricted to decomposition group at P is semi-simple. Well, at least for GLN, it's clear what I mean by that. So in this case, we make the following conjecture. Well, I should say something first, Namely, in this case, if rho bar is restricted to decomposition at P is semi-simple, one can write down certain crystalline lifts, as in the example for GL2 before. So one can, in this setting, then one can define, or one can maybe, it's better to say one can write down certain obvious crystalline lifts.
Sorry.
Yes?
So, is it easy to prove or hard to prove that there exists any crystalline lift? Do you have a mod P representation?
In general,
Yes. Is it true?
I don't think it's easy.
So is it true?
Conjecturally, it's true.
Okay.
But in the semi-simple case, you agree that it's that one can write down certain lifts. Maybe I should say something about GLN just to give the flavor of what I mean by obvious crystalline lifts. But it's similar to before, that in that case, rho bar restricted to decomposition at P is a direct sum of inductions of characters. Let's say chi I, and then one can lift, so maybe I equals 1 to R, and then one can lift characters chi I to crystalline characters, maybe of different Hodge state weights, and then one gets, for GLN, if the tame exponents of rho bar restricted to inertia aren't in any boundary sort of cases, like the boundary case I mentioned before for GL2, then in such a generic case, one can write down n factorial crystalline lifts up to sort of trivial modifications by adding sort of p minus 1 to exponents or something like that. And then the explicit version is the following, that if under this assumption that rho bar restricted to decomposition at P is semi-simple, then the weight set of rho bar is the smallest set such that on the one hand it contains the Serre weights that correspond to the obvious crystalline lifts under conjecture A, to the obvious crystalline lifts via conjecture A. So for GLN, one would generically have n factorial of those. But then this set of weights should also satisfy conjecture B. So in other words, whenever conjecture B gives you an implication of one weight to another weight, this should be satisfied for the conjectural weight set. So in this way, you get the smallest possible set by just starting with the obvious ones and then taking all further implications from conjecture B. And in general, for GLN, one actually gets, in the end, one gets a lot more weights from this second point than n factorial from the first. And the theorem is that when G restricted G over QP is GLN, then this conjecture above the explicit version agrees, at least generically, with the earlier conjecture, or the earlier conjecture of the speaker. I don't know how to put that. So what do I mean by generically? I mean, again, if one starts with a rho bar restricted to decomposition at p semi-simple, such that the tame exponent on inertia are not close to any boundaries. So more concretely, I mean by that let's say if we're in the niveau 1 case, we have omega to the a1 up to an, I mean that the differences of the ai's are not too close to being a multiple of p, or p minus 1. And this earlier conjecture was of a completely different kind. It described the weight set of the conjectural weight set of rho bar, not in terms of crystalline lifts, but in terms of a certain Deligne-Lustig representation, which is naturally associated to rho bar restricted to inertia at p. And then it's actually not. It's kind of surprising that in fact one can show that. I mean, it's sort of easy for this one, but this one was not at all obvious that it would work out. But in fact, generically, it does. And this same argument should actually generalize to whenever should not just work for GLN, but whenever both conjectures apply. So that it should work whenever the group is in addition has connected center, and whenever the local field instead of QP is unramified over QP. And finally, I want to mention that when G, now even over some extension field, G over, if K is if we now work with a number field K, but if G over each completion at each place at P is isomorphic to GL2, in that case, generically, again for generic rho bars on inertia at P, this conjecture is compatible predicts the same weights as with the conjectures of Basser-Diamond and Jarvis for Kp over Qp unramified, or K over Q unramified at P, and shine in general. But as I said before, in this case, one doesn't have, I mean, every weight is sort of an obvious weight. There are no further implications by conjecture B. And I'll stop here.